What's up, Algebra 2? This is lesson 3.7. We're talking about determinants and also using determinants to solve systems of equations, and we call that using Cramer's rule. First of all, a determinant is just a number that's associated with every square matrix. So associated with every square matrix. And it's denoted in two different ways, either like this, the det of A, or like this with straight lines being the determinant of A. Now in 2x2s, it's fairly simple. It's just the product of the main diagonal, and then you subtract the product of this upward main diagonal from that. So AD minus that CB. Okay, so those are not too bad. Those don't take long at all. 3x3s take a little bit longer. And notice if you just rewrite these first two columns outside, notice that ADG, ADG, BEH, BEH. You take the main diagonals going down, and you find those products. So AEI, it's right there. Next main diagonal right here. Next main diagonal right here. So you sum those three up, and then you do the upwards diagonal, this, and then you just, so you sum those three up, and then you subtract the first one minus the second one. Alright, so let's try some here. This one's going to be 3 times 1, which is just going to give me 3. Then subtract this product. 6 times a negative 2 is a negative 12. So it's going to be 3 plus 12, that would equal to 15. The determinant of this 2x2 matrix is 15. On the second one, notice I've redrawn it down here, and I just rewrote those first two columns outside. So I'm going to go with the downwards diagonals here. 4 times the negative 2 is going to give me negative 8. The product of these three is going to give me 0. The product of these three, well, 2 times 3, or 2 times negative 3 is going to give me negative 6, times 5 is going to give me a negative 30. And I'm going to subtract from that upwards diagonals. So those three, which is 0. 5 times 4, which is 20, so it's going to be negative 20 because I'm multiplying by that negative 1. And then these ones, which is going to be 3 times 1 times negative 1, so it's going to be positive 3. So simplifying this down, this is going to be negative 38 minus a negative 17. Negative 38 plus 17 is going to be 1, negative 21. It's going to be the determinant of that 3x3 matrix. Alright, now using the determinant, someone's discovered that you can use that to find the area of triangles. So if you have triangles with these coordinates x1, y1, x2, y2, x3, y3, you can plug those points into a 3x3 matrix where this third column is just ones, multiply that by the half, and then you obviously have to take the positive version of that. So sometimes the determinant is going to be negative, sometimes it's going to be positive. So if you take the positive version of that, then you'll get this. So notice here I just took these 3 points that they gave us and plugged them into this matrix here. 5 times 2 times 1 gives me that 10. 11 times 1 times 1 gives me that 11. 1 times 9 times 3 gives me that 27. So I'm adding those three up, subtracting these purple ones. So 1 times 2 times 1, which is 2. 3 times 1 times 5, 15. 1 times 9 times 11, that's 99. So 48 minus 116, negative 68. Half of 68 is 34, and I want the positive version of that. So the area of this triangle with the vertices here, here, and here is 34. Notice we didn't have to find base, we didn't have to find height, we didn't even have to graph this thing at all. We were able to find the area of that just simply using determinants and matrices. Alright, so now is where we come to Cramer's rule. And Cramer's rule is called Cramer's rule because there's a mathematician who used this method to solve systems of equations. So remember, thus far, we've been solving some systems of equations in this form, maybe by graphing, or by substitution, or by elimination. And so here's another way we can do that, and that's with Cramer's rule. First of all, we make what we call a coefficient matrix, and it's just the coefficient matrix is just A, B, C, D, based off of this generic version here. So for ours, 3x minus 4y, here's that 3 and that negative 4. And then 2x plus 5y, there's the 2 and the 5. Okay, so the yellow ones I've highlighted here are the coefficients of the y coordinates. The green's the coefficient of the x coordinates. Now, you'll see that you can solve for x using this and y for this. Notice on the numerator, it's the determinant of this coefficient matrix here, but instead of the column, like since I'm solving for x, instead of the x column, I use the constants over here. When I'm solving for y, instead of using the y column of this, I use the constants over here. So notice before I jump into solving for x and y, I came over here and found the determinant of a, which is 3 times 5 minus 2 times negative 4. It's going to be 23. So I'm using that as my denominator because it's the determinant of this A matrix. So my denominator is 23 because that's the determinant of A, either way. So if I want to solve for x, I'm going to use the y coefficients here, the negative 4 and the 5. I'm going to use the constants here and the x's. So then I just need to find the determinant here on the top. So it's negative 15 times 5, which is negative 75. 3 times the negative 4, negative 52. Subtracting that, I get negative 23 over 23, which just simply gives me negative 1. On the y's, again, I'll use the x coefficients here, because I'm trying to find y, so I'll replace the y coefficients with those constants. Again, the 23 is down here from over here, the determinant of A. 3 times 13 is 39, 2 times negative 15, negative 30. When I subtract them, I get 69 divided by 23, and so then I get the answer of 3. So then my answer to this, again, is a point where those two lines intersect, which is where x is negative 1 and where y is 3. Alright, now for 3 by 3 matrices, it's a little bit longer because those determinants take a little bit longer. However, the process still follows the same thing. So this coefficient matrix, the A, is still just the coefficients from the x's, from the y's, and from the z's, and then over here those constants. Okay, and then when you're solving for x, it's still the determinant of this A on the denominator for all 3 of those. And then whenever you're solving for x, you replace those constants into the x column. If you're solving for y, you replace those constants in the y column. If you're solving for z, you replace those constants in the z column. And the rest of it stays the same. So what takes longer in this is just finding those determinants. And I worked them all out by hand, but there are online calculators that you could use to find the determinants of 3 by 3 matrix. So you can just put in the matrix and it will give you out the determinant. So thankfully for us, the determinant of A worked out pretty nicely to be 19 minus 18, which is just simply 1. So it made our life pretty easy. So we really just have to figure out the determinant on that top one, okay, which is a 3 by 3 matrix. If you want to go through and check my math, you can do that. 18 times 1 times 1, 18, 4 times 3 times 11, 220, etc. So you just kind of work those out. Right, those are down, the main diagonal is going down, main diagonal is going up, works it out to come and be that negative 28. This comes to be negative 28. Again, the denominator is just 1, so my x is negative 28. Something similar for the y's. Work this all out. Again, feel free, please double check me, pause this, check where I got these numbers. becomes to be this minus this, comes out to be 14. Z comes all the way out to be 56. So my final answer is going to be that coordinate point that has negative 28, 14, 56. Now, is this long? Yes, I agree it's long. However, I'd probably say this might be a little bit shorter than maybe trying to figure this out by substitution or by elimination method. Take your pick, whichever one you think is easier, unless, of course, I tell you to do it specifically by this way. So there you go. There you go. Again, feel free to pause this and check my work on this.